faults, identification of faulty phase, estimation of severity level, and conclusions and future scope in this area. So coming to the introduction, AC motors plays a major role in modern industrial applications. So out of that, the squirrel cage motor are the most commonly used electrical drives in many industries due to their low cost, ruggedness, low maintenance, and operating with easily available power supply. So because of this reason, we require the stresses which will influence during their industrial operation. So most of the times the industrial motors are exposed to the various non-ideal operating conditions due to their abnormal operating conditions and system conditions and environmental conditions. So because of these conditions, the machine undergoes various stresses. So thermal, electrical, and environmental stresses. So the thermal stresses is mainly causes due to the abnormality in the system conditions like under voltage, unbalance in three-phase, single phasing, low frequency, high frequency operations. Similarly, due to overloadings and insufficient lubrications given to the mechanical parts also will leads as a thermal stress in the operating machines. So the other part of stresses is the electrical stresses. These are majorly due to the frequent startups and frequent switchings and momentary interruptions and bus transfers. The mechanical stresses is mainly causes due to the switching bearings, incorrect alignments, incorrect fixing of couplings. So because of these problems, the rubbing is happen between the mechanical parts, which will cause the mechanical stress on the system. So in view of all these things, we require a correct operation of the motor. So that leads always the failures and finally causing the production curtailments. So what are the major failures which we observe on the various parts of the machines is, with refers to the origins, the faults may be as a internal as well as the external. So the internal faults is again categorized into two types, electrical faults and mechanical faults. The external faults are categorized into supply side faults and mechanical overloads. So the electrical faults is happen in the parts of stator and rotor of the motor. The stator faults are the turn faults, phase to phase fault, phase to ground. Rotor faults are the broken bars and end rings. So in case of squirrel case, it's a broken bar faults. In case of slip ring induction motor, that rotor faults is related to the end rings faults. Coming to the mechanical faults is classified into two types, bearing faults and air gap eccentricity. So the bearing faults is happen due to the less and excess lubrications, high seal friction. The air gap eccentricity is happen due to the static eccentricity and dynamic eccentricity. So external faults are supply side and mechanical overloads. The supply side is the single phasing, under voltage, unbalanced faults. So coming to the industry requirements, in any industry, basically the peoples require the certain maintenance. So the maintenance procedures which follow in the industry are the three types. One is the corrective maintenance. The second one is the time-based maintenance, and third one is the condition monitoring. The corrective maintenance is always follows when the failures happen in the system. So because of that, the maintenance of that is very low. The maintenance cost related to that operation is very low. But it gives the unaccepted downtime. So in case of time-based maintenance, the maintenance is performed at a fixed interval of times. The cost due to that maintenance is high, but it reduces the unaccepted downtime. So whenever the unexpected downtime is reduces, the production cost is increases. So because of that, the time-based maintenance is essential for the large industries. So the third technique for the maintenance procedure is the condition monitoring. In recent industries have shown much interest towards the condition monitoring because it reduces the consequences in the damages, increases the mission life, reduces the spare part inventory, reduces the break time. So because of these advantages, in recent years, the industries have shown much interest towards the condition monitoring. So according to the survey reports, the fault diagnosis techniques must be classified into two categories. So whenever we require the condition monitoring for the industries, so we required a certain diagnosis techniques. So according to the reports, those diagnostics techniques is the model based or model free. So the model based techniques is found based on these three methods. So based on the data based model, analytical model, knowledge based model. So based on these models, we implement a model and make use of that model. We monitor the systems and diagnose the various disturbances on the system. So coming to the model free system, that model free system required these things: measurements, features extractions, and classification based on certain criteria. So they have a certain advantages and disadvantages for the model based as well as the model free systems. So the model based approaches are built based on the data retrieved from the process under the steady state. Analytical model is always found based on the physical interaction, and knowledge based models is developed based on the human knowledge. But the correctiveness of that system is not accurate. So because in these cases, the residuals never become zero because of the presence of noise exists in the models. So that error will give us as the fault identification in a improper way. That means even if there is no fault, but the system will give a fault because of the model error. The developing of model based methods is very complicated, time consuming. Even sometimes it is unfeasible if system is more complex. So because of that, nowadays most of the approaches is followed make use of model free approaches. So this model free approach carries by monitoring the processing system. That monitoring the processing system of information is given to the certain signal processing techniques So like Fourier transform, fast Fourier transform, short time Fourier transform, wavelet transforms, like that. Certain signal processing techniques is help to extract the information which we require for the analysis. So the next stage of operation is identification of fault. The next stage of process is the identification of fault and then classification of the fault. But the cost of implementation of this model-free system is costlier than the model-free system, but it gives a more accurate results when compared with the model-based systems. So this exhaustive literatures inferred that the majority of the cases, the diagnosis scheme should be sensitive to the operating system. So whenever the operating condition of the system is changes, the scheme is influenced by the operating condition. So the second point is the sensitivity of the fault detection and identification is improved by integration of concepts of artificial intelligence techniques with the signal processing techniques. So whenever we require the efficient detection algorithms, we go with the integration of the analyzing techniques. So that means signal processing techniques is integrated with the artificial intelligence techniques. So the performance of such integrated concepts will give the better than the individual processing techniques. Identification of fault in presence of supply voltage unbalance and detection of faulty phase have been attempted in a limited manner. And most of the schemes, the validation is applied for a single rating missions. And single reliable procedures is not applied for the multiple faults with the help of non-invasive signals. So because of this, to fulfill the gaps, we follow the objectives. So these are the major objectives for the today's sessions. So the objectives is developing a model and create various faults in MATLAB Simulink environment, validating the model through experimentation, developing a model and creating the faults and diagnosis those faults. After that, validating the proposed fault diagnosis algorithms through experimentation data along with the simulation data. Integrating the signal-based and AI-based analyzing methods and classify the faults, identify the faulty phase and its severity levels. So these are the objectives. So based on those objectives, this is the structure for implementing the objectives. The first one is the model, the second one is the analyzing method. So whenever we require the model, that model is valid for the low to high frequencies. Because whenever we created the fault, on the system, that fault is a transient condition. So during the transients, the frequency component is high. So because of that, the model must be a low to high frequency model. Under normal condition, the frequency of the system is the 50 Hz. So whenever the disturbances happen on the system, that frequency is varying. So that variation of the frequency is low to high. So because of that, the model needed for analyzing the faults, we require the distributed high frequency model. That we have to validate with the help of simulation as well as the practical readings. Similarly, we analyze the faults, make use of this model and classify those faults, make use of the wavelet and MM classifier. So coming to the modeling of three-phase induction motor, the model we represent for the systems is two types. One is the low frequency models, another is the high frequency model. The low frequency model is nothing but as the lumped parameter model. As for the standards of IEEE, that model is, we call it as the 112. So the behavior of the motor under low frequencies is described, make use of this lumped parameter model. This lumped parameter model is used for the analyzing the behavior of the motor under low frequencies. So whenever we require the transient operations on the system or the transient operations of the motor is analyzed, we require a distributed parameter model. Distributed parameter model. So generally this distributed parameter model is used for the medium to high frequency range of analysis of AC motors. So whenever we require the behavior of the motor under transient conditions, we require the medium to high frequency models. So compared to the low frequency model, the distributed high frequency model requires the extra elements such as stator to frame resistance, capacitance, and stator to slot capacitance. That we all call it as the stator turn to time winding capacitance. This is the capacitance related to the slot and resistance related to the slot. This is slot to frame resistance and capacitance values. So whenever we go with the distributed parameter model, in addition to the lumped value, the additional parameters is this. One is the slot capacitance value. Second one is the slot resistance value. Another is slot to frame resistance value, slot to frame capacitance value. So for these parameters, we incorporated in the circuit and analyze the faults on the three-phase induction motor. So either it's a turn level or coil level. So how to achieve this distributed parameter of the stator resistance, stator winding resistance, stator winding capacitance, stator slot to frame capacitance, stator slot to frame resistance. This values is computed, make use of two setups. One is the differential mode test setup and another is the common mode setup. So apart from the distributed parameter, the lumped parameter is estimated, make use of no load and blocker rotors test. So in the third year laboratory itself, you can know it as how to compute the lumped parameters of the induction motor. So that is the stator resistance, leakage resistance or leakage inductance of the stator, rotor leakage resistance, rotor resistance, core resistance and magnetizing inductance values. So these components we obtained from the no load and blocker rotor test. So apart from these parameters, we require the additional parameters in the distributed parameter model. So those parameters is achieved by using differential mode test and common mode test. So what is this differential mode test? So this differential mode test is nothing but as the measurement of impedance under this operation, under this test operation. So differential mode means the measurement of impedance is between the two terminal. One is the phase A, another is the tied leads of phase B and phase C. Tied terminals of phase B and phase C. So that measurement is practically possible with the help of LCR meter of 20 Hz to 1 MHz of range. So here we are using the Agilent 16089A model for the range of measuring of frequency variation is 20 Hz to 1 MHz. For different intervals of frequencies, we measured the impedance value and plotted that impedance curve between the magnitude value with frequency changes. So make use of the obtained parameter we make as the differential mode circuit in the MATLAB Simulink platform. So this is the circuit for representing the differential mode simulation circuit of 5 HP induction motor. So this is the setup, practical setup of common mode test. This practical setup for the common mode test is happen for measuring the impedance by connecting the probes between the terminals of ties of phases of ABC and ground. So this will give us as the capacitance value corresponding to the stator to frame, and this is given by the information of slot to slot capacitance. So these two tests will give us the values of parameters which are additional to the lumped parameters, that is RSW, CSW, CSF and RSF. So those values is obtained by conducting the common mode test and differential mode test. So this is the simulating diagram for the common mode test. These are the estimated parameters corresponding to the no load block rotor test and differential mode and common mode test. So anyone is interested to do this experimentation, then you follow a paper that name or title as Universal Parameter Estimation of Three-Phase Induction Motor. So that is the title. So based on that paper reference only, I computed these parameters. So coming to the validation, so whatever the parameters we computed from the differential mode and common mode, so those parameter values is incorporated in the model which developed in the platform of MATLAB Simulink that compare with the impedance plot with the practical measured value with the help of LCR meter in the common mode test as well as the differential mode test. So these are the comparison of measured and simulated response of impedance versus frequency in differential mode test. So DM of value which we have measured practically indicates a dark line. So that slip value corresponding to the dark line is equal to 1 In simulated mode, we can change the slip value by changing the value corresponding to the S. So initially I incorporated the S equal to 1 and simulate the result. That will give us the this gray color line. So the gray color continuous line and dotted line of gray will give the slip value of 0.04. For higher values of slip and lower values of slips, there is no change in the impedance plot. So the impact during the high frequencies is very negligible on the slip variations. So similarly, we compare the measured and simulated responses in the differential mode test also. So there is a slight variations we observe between the simulated and measured values. So why these things is happen? So we can conclude finally at the end of this process of modeling. So valid for 5 HP induction motor. So this is the validation for 5 HP induction motor for common mode measured value and common mode simulated value. Similarly for phase value, this is phase value. Excuse me. So this figure shows the practical setup for 3 HP induction motor. These are the estimated parameters. So the simulated results is compared with the measured values. So there is a slight variations at certain frequencies. So other than the measured and simulated values is almost equal. So coming to the conclusion of this modeling, the deviations in the observed from the figures is mainly due to the distributed level mentioned in the simulated model. So the distributed level mentioned in the simulated model is a coil level, but practically the mission is at turn level. In practical, the mission is at turn level. So because of that reason, so we get a slight deviation in the simulated values with practical results. So another point is the core magnetizing inductor is a constant in the simulation model, but practically it's not constant. Practically it is not constant. So even these two impacts also we can indicate that the frequency response in the simulated slide is closely matched with the response measured in the practical missions. So the model is valid for analyzing the faults. So any fault detection must require a proper screen to identify the faults. So that identification needs a certain features. So because of that, we required a certain analyzing technique. That analyzing techniques extract the features. That extracted features will train the system and gives the better performance. So for that process, we required a certain detection scheme. So with the advancement of more powerful computers and sophisticated electrical mission models, there is a possibility to design and analyze the transient behavior of the motor. So because of that, we model that. So that model system is we have to consider and analyze the faults. So for that purpose, we require the certain signal processing techniques. So with the rapid development of signal processing techniques, the stationary signals is analyzed based on the spectrum techniques of Fourier transform, fast Fourier transform, and short time Fourier transform. So unfortunately, all these methods are not suitable for non-stationary signals. So what is the meaning of stationary and non-stationary signal? Stationary means you take a certain window, in that window we have only a one frequency. So those frequency we can obtain, make use of Fourier transform and fast Fourier transform. Or the frequency changes happen in that window at one place. It's not in multiple places. So at one place it's happened. Clearly the FFT analysis of Fourier transform will give the which frequency component exists in that signal. So the signal contains a certain frequency component. That component information is given. But at what instant that frequency component happen in the signal, that information is lost by the Fourier transform and fast Fourier transforms. But short time Fourier transform, it's a windows based technique. So because of that, it gives the information regarding a short window. So approximate time instant is also given. So if the information regarding the frequency component and time instant, both the information is not given by the Fourier transform and fast Fourier transform. At some extent, this short time Fourier transform will give it. So non-stationary signals means it's continuously varying the frequency component in the signal. So in such cases, that information of time instant regarding the continuous changes of the information is not given by the spectral analysis of Fourier transform, FFT, and short time Fourier transform. So in order to solve this, we need the multi-resolution analysis technique that we all call it as the wavelet transform. So wavelet is a kind of variable window technology. Wavelet is a kind of variable window technology. It means the signal analysis is possible both time as well as the frequency. So that's why we call it as the wavelet transform is a multi-resolution analysis transformation. So when the signal is we analyzed in the time domain with continuous, so then that wavelet transform is we call it as the continuous wavelet transform. So when the signal is a decomposed signal, so then the signal is a discrete. Because of that, we apply the wavelet to that discrete signals. We call it as a discrete wavelet transform. So always in the fault diagnosis schemes, the captured signal is discretize the signal, because the continuous signal will have a more samples when compared with the discrete signal. So the less number of samples we have to consider and process the signal is more easier than the continuous signal of analysis. So because of that, we go with the discrete wavelet transform instead of continuous wavelet transform. So here we go through with the scheme of discrete wavelet transform to analyze the signal. So here the detection algorithm is proposed based on the multi-resolution analysis with the consideration of three-phase currents. So these three-phase currents is a non-invasive measurements. So because we don't need it to hold the machine to put the measuring devices. So in case of vibration signal or temperature measurement, we need it as the sensors placed on the either inside the frame of the induction motor or outside the frame of the induction motor. But three-phase measurements of currents is not needed as the any disturbances or any abstracts given to the motor frame. So that's why we call it as it's a non-invasive measurement technique. So in this technique, the number of measurements is only 3. So those 3 are the three-phase currents. So once we consider the measurements and we sample those measurements to take it as the discrete signal. So sample the captured signal at a sampling rate of 6 kilohertz and analyze that signal with the help of wavelet mother wavelet of Bayer 5.5. So whenever the disturbances happen on this motors, the high frequency component is exist. So to identify that high frequency component, we require the detailed coefficients. Every mother wavelet, when we are analyzing that mother wavelet, will give us the 2 components. One is the high frequency component and other is the low frequency component, because the signal is processed through the 2 filters. One is the low pass filter and other is the high pass filter. So whenever we send the wavelet to the low pass filter, we get the approximate coefficients. When the signal of wavelet is processed through the high frequency, then we get the detail level coefficients. So in this detection algorithm, we consider a moving window of 10 samples of detail coefficients. So those detail coefficients of absolute peak value is set as a fault index. So the maximum value of 3-phase absolute peak values is defined as the fault index. So when this fault index is compared with the free defined threshold values to identify the faults. So when we identify the fault, immediately we get the time instant also, because the wavelet is a multi-resolution analysis. So this is the detection algorithm steps we follow for identifying the fault or detect the fault. So these are the capture 3-phase current signals under healthy condition of 5 HP induction motor. So here we are looking the current signals. So it's a 3-phase currents. Because of that, each other is apart from 120 degrees. There is no abnormality and there is no supply side disturbances. There is no noise exist in this signal. So because this signal is we captured from the simulated file. So in the simulated file, we don't have any noise. So practical system will get the noise measurement also because of vibrating of the machines or due to the noise given by the measuring devices. So every thing will introduce some noise to the captured signals. But here there is no noise. It's a clear waveform. So we can clearly see it as all the peaks values of 3 phases are equal. and each other is displaced by 120 degrees apart. So it's a healthy condition. So this capture signal is sent to our algorithm and identify the detail level coefficients for the healthy case. So there is no disturbance. So because of that, there is no high frequency component present in the signal. So that's why the detail level coefficient corresponding to the signal is 0. So the coefficients is always generated with the help of mother wavelet correlated with our signal. So here there is no disturbances. Because of that, the correlation value is 0. There is no correlation. So the correlation values is 0. So that's why the detail level coefficient values we get as the zeros for the healthy case. So the detection algorithm is always check with the fault index with the predefined threshold. This is the threshold value. So this fixing of threshold is based on the various studies performed on the design model with the peak values of the fault conditions and peak values of the healthy conditions. So in between that we consider as a threshold value. So based on that, this is our defined threshold. So under healthy condition, the fault index value is 0. So that is below the threshold. So here we are not saying any fault index value. That fault index value is 0 level. So the next, we look this figure as a case of two-turn fault in R phase of a 5 HP induction motor. So these are the current signals. So the fault is created at the instant of 60 milliseconds. So after the default values, the fault is happen on OR phase. So because of that fault in the OR phase, the current value slightly rises. But here from the observation of the waveform, we can't predict that variation because it's a incipient fault, low turns fault. So incipient faults cannot visualized in the time domain. So because of that, we need as a frequency domain analysis, time frequency domain analysis for finding the fault disturbance value and its location. So because of that, we analyze the signal under wavelet transform. So when the signal is sent to the wavelet transform, the decomposed value of detail level, D1 level coefficients is this. So at the instant of here, we observe as a value corresponding to the detail level coefficient because the mother wavelet of Bahadgar 5.5 is correlate under the disturbance and give it as the certain coefficient values. The maximum correlation is given at the instant of this. And the peak value corresponding to the OR phase is higher than the remaining two phases because the fault is in the OR phase. So why this Y and B is affected? So when the fault is happen in the OR phase, that impact is on the Y and B also. Y and B also. Because it's a distributed model. So whenever the interturn fault is happen in the OR phase, that interturn fault will create the disturbances through the stator to frame capacitance. Stator to frame capacitance on the other healthy phases. So these are the impact. So one phase current is increases, other two phase currents is decreases because of the fault in R phase. So the estimated value of fault index corresponding to this two-turn fault in R phase is this. So this fault index value is crosses the threshold value. So because of that, the fault is identified. So the similar studies is studied with the help of simulated model with the various switching instant. So the switching instant is changes over a full cycle, but here the plot indicates as a off cycle. So whatever this is switching instant is changes in the off cycle, the similar impact is in the remaining off cycle, because we consider the fault index values is a absolute values of peak of three phase detail level coefficients. So because of that, we plot the variation in fault index for an interturn fault on coil 1 over a period of 180 degrees volt. So with a gap of 45 degrees. So this is the three-phase currents for a LG fault. So the line to ground fault is created in the phase of OR of a 5 HP induction motor. So whenever the line to ground fault is happen, immediately that phase value corresponding to the OR is abruptly changes when compared with the other two phases. So it's a higher fault when compared with the interturn faults. So interturn faults is the basic insulation failures of the winding. So when we are undetected as the interturn faults, those faults is leads phase to phase fault. That phase to phase faults leads the phase to ground faults. So because of that, we study all the types of faults. One is the interturn fault, another is line to line fault. The third category of fault is the line to line fault. So line to ground, interturn, and line to line fault. So in the line to ground fault happen in the OR phase of 5 HP induction motor. The current magnitude is shoots abruptly when compared with the remaining two phases. So that we are observing in the detail level coefficients of LG fault. So the detail level coefficients in the three-phase currents also we can observe the same information. The magnitude corresponding to the detail level coefficients of R phase is very high when compared with the Y and B. So based on this magnitude value, we can segregate the few turn faults with the line to ground fault. So here the fault index value is also crosses the threshold, fault is identified. And which phase the fault is happened, that can also we can identify from the which phase will have a maximum value of peak absolute of detail level coefficients. So this is the variation of fault index for LG fault on a coil 3 with the switching instance of 45 degrees of step. So the next fault is the line to line fault. So whenever the line to line fault is happen in the system, immediately the change we identify for the fault currents is the lines of which is undergoes the faults, those lines of currents is 180 degrees phase shift. So here we created the line to line fault between the R and Y phases. Because of this, the R and Y phases is 180 degrees of phase shift. So exactly IR is 180 degrees of IY. And this same information we can observe, make use of detail level coefficient also. If R phase detail coefficient is negative value of peak, then Y phase detail coefficient is positive value of detail coefficient. So here this is negative peak, this is positive peak. So both are opposing each other. So but the detection algorithm is based on the fault index. The fault index is we consider from these three detail level coefficients. So the absolute peak values of maximum peak absolute value of the detail level coefficient of three phase is set as fault index. So when that fault index is crosses the threshold, the fault is identified. So here the case also the fault is identified because the fault index is crosses the threshold. So the efficacy of the algorithm is we check with the help of variation in fault index with respect to the incident angles. So because of that here the case also the incident angle is changes at a step value of 45 degrees. So another fault which related to the supply side of the induction motor is the single phasing fault. So whenever we create a single phasing fault, that corresponding phase of current becomes 0. So here R phase is out and remaining two phases is under connection. So whenever the single phasing fault is happen, immediately the other two phases of currents is 180 degrees of phase shift. So that also we can observe through with the help of these figures. So these are the detail level coefficients. The next one is the 30% of under voltage. So we create the under voltage disturbance on the three phase induction motor. So which is created with the help of 30%. So how do you create this under voltage? So the voltage corresponding to the system is, let us we take it as the 440 volts of line to line value. So one phase of value we are take it as the under voltage. That is not the case here. Under voltage means all the three phases undergoes the under voltage. So that under voltage means all the three phases is suddenly dip its values to the percentage of 30. And it's continuously sustained for a long duration of period. Then that voltage is we call it as the under voltage. So whenever we create the under voltage on the phases of R, Y, B suddenly, so this will be happen because of sudden load applied to the systems. So whenever the sudden load applied to the system, immediately the voltage applied to the system is decreases. So due to this disturbance also we can analyze the detail level coefficients, and the fault index value of this detail coefficient is crosses the fault index. So the next type of disturbance is the supply unbalance. So there is an unbalance in one phase. So that unbalance corresponding value in terms of supply voltage is 10%. So that supply unbalance corresponding variation in currents we are observing here. So whenever the supply goes as the unbalance, so there is a rise in temperature of that corresponding phases. So whenever the temperature is rises, there is the resistance value corresponding to the winding is decreases. The decreased value of resistance in that particular phase rises the current. So that rise value of current again rises the temperature. So that rise value further reduces the resistance. So like that, this cumulation action is happen in the system, and this unbalancer leads as the damage in the interturn some cases. So because of that, the early identification of supply unbalance is also essential for condition monitoring. So these are the detail level coefficients for the 10% of supply unbalance. These are the variations corresponding to the fault indexes for various faults. So all the cases we observe here, the fault index values is above the threshold. So that means the detection algorithm is effectively detect the faults. Effectively detect the faults. So all these things we observe with the help of simulating files only, but practical signal we cannot take it and process through this algorithm. So whenever we capture the signal or we introduce some noise to the simulated signal. So this is the three-phase current for the stator interturn fault under noisy condition. So with the help of MATLAB, so we introduce a noise with the help of seed values. So introduce the noise, then we can observe as this waveform is not a smooth. It's not a pure sinusoid. It's having some destructives in the path of sinusoid, but it's similar as a shape of sinusoid. So to check the effectiveness of the algorithm by taking the noise injected signal. By taking the noise injected signal under two-turn fault in R phase condition. So when this signals is analyzed with the help of proposed algorithm, these are the detail level coefficients. So can you observe any fault instant here? Because the mother wavelet is correlated with the noise and give it as the coefficient values. Those coefficient values is equal to the fault disturbance coefficient values. So because of that, we see it as the continuous variation of the coefficients. That means the noise level frequency is matched with the fault level frequency of two turns. So that's why the algorithm is not identify the fault instant. And the entire interval is represented as a fault. So that means the fault is happened at the 0 degrees of inception at the after 60 milliseconds, even though the fault index values is given as the certain values, every instant that value is higher than the threshold. So whenever the noise is incorporated in the signal, the detection algorithm is failed to identify the fault instant. So that means this DWT scheme is inefficient under noisy condition. Under noisy condition. So because of that, we require the another algorithm which will effectively detect even under the presence of noise. So for that purpose, we use the SWT and DWT. What is the meaning of SWT? SWT is a stationary wavelet transform. So discrete wavelet transform means the signal is passes to the two filters. One is the low pass filter and another is the high pass filter. So the DWT information is we always get it at the level of 1, 2, 3, 4. The samples is down samples. So that means the samples becomes off, off, off. But in SWT technique, the samples never down samples. So with the zero padding technique, so whatever the samples exist in the signal, the same amount of samples we get it in the detail coefficient as well as in the approximate coefficient. So because of this convolution, the information exists in the signal never lost. Never lost. So that's why we go with the SWT technique for reconstructing the signal. So whenever we have to reconstruct the signal with DWT, because of downsampling, the certain information is lost. But in the SWT, we never lost. Why we need the reconstruction? So in the earlier algorithm, so what we have to see here, whenever the signal is having the noise, the algorithm is unable to identify the faults and its instance, fault and its instinct. Even LD case is also, LD portion of the instant also treat as a fault, but actually the fault is happen at the instant of after 60 milliseconds. After 60 milliseconds. So for that purpose, first we have to require as the elimination of the noise present or exist in the signal without corrupting the feature related to the fault. So like that, we have to reconstruct the signal. So that reconstruction process required the stationary wavelet transform. And decomposition, we again use the DWT, but the reconstruction process, we use the SWT. So make use of these two wavelets. We again build an algorithm. The steps we proposed in that algorithm is capture the signal with a sampling frequency of 6.6 kilohertz. Analyze the signal with the stationary wavelet transform of about 5.5 mother wavelet up to 6th level. Extract the fault feature by taking the level-based threshold values. So whenever we are reconstruct the signals, certain unrequired information is removed from the signal with the help of thresholds fixes for the every level. So that thresholds we fix it in the SWT is 6th level of detail coefficients is calculated by making use of mean value of first cycle multiplied with the distortion factor. And remaining all coefficients set or equal to maximum value. So why we are remove all the coefficients corresponding to the up to the 5th level? So that 6th level detail coefficients only contains the information of 0 to 300 heads of component. 0 to 200 or 0 to 300 heads of component. So that component of information is essential for extracting the fault feature, not other than the remaining frequencies. So the noise level frequency is never superimposed with the fault feature if we are considering like this. So make use of these thresholds, we reconstruct the signals and apply the inverse stationary wavelet transform. That reconstructed signal is, we call it as the fault residue. And again, this fault residues of three-phase currents is analyzed with the discrete wavelet transform up to the level of 4th. Up to the level of 4. So again, the fault detection, we consider the detail level coefficients of its derivatives. We call it as the slope of detail level coefficients. So those slope of detail level coefficients is we compare with the adaptive threshold. So the disturbance is identified by checking the sum of absolute values of three-phase detail level coefficients of derivatives with adaptive threshold. So adaptive threshold means according to the the changing of machine loading conditions, the threshold value is also changes. So that means according to the operating condition, the threshold values changes. So every moving window, we compute the adaptive threshold value. So that moving window of adaptive threshold value is we take it and compare the fault index with the adaptive threshold. So according to the operating condition changes, the threshold value is also changing. So that's why we call it as the adaptive threshold value. So the algorithm is improved with the incorporating of this adaptive threshold scheme, and the reliability of algorithm is improved by checking the count values of 3 consecutive samples. 3 consecutive samples. So what is this count? Count means, so when the fault index value is crosses the adaptive threshold, then count will gives 1. So every sample point we compute that fault index over a window of 10 samples. How many count values is crosses the threshold? How many fault index values is crosses the threshold? That many values is represent as a count. So 3 consecutive samples of fault indexes and its value should be greater than 6. That means the count corresponding to the 3 consecutive samples of fault indexes. So the moving window size is 10. So let us we take as a window and represent as the features. So according to that, the count values we start counted for a window of 10. So all the 10 samples of fault indexes crosses the threshold, then the count value is 10. So next, the moving window is moved by 1 sample. Again, the count value is computed. So again, the moving window is moved by another sample. And again, count values computed based on the fault index and threshold crossing points. So that count value should be greater than 6. So then that is treated as a disturbance. Otherwise, it's not a disturbance. So the disturbance instant is given by the crossing point of threshold in both the checking logic. So the disturbance is detected by taking the difference of fault instants. So this is the algorithm. So we follow the fault instant identification and fault identification. So the fault detection and its instant identification is find out, make use of this flow chart. So the flow chart will give the information of captured 3-phase current signals. So those are processed through the SWT for reconstruction. So once we get the reconstructed values with the help of level based thresholds, we again decompose that reconstructed signals through DWT. Then we compute the slope of detail level coefficients and find the fault index. So which is compared with the adaptive threshold to identify the count values. So once the computed count values for 3 successive samples is greater than 3, then the fault is detected and location is identified. So these are the mathematical equations we represent for the fault index. So this is the fault index. So that is absolute value, sum of absolute values of slope of detail level quotients of reconstructed signals. So this is the calculation of threshold value. So here we computing the adaptive threshold. That's why we write down this formula. So the adaptive threshold value is computed, make use of this. So what is this mathematical equation indicates? The adaptive threshold is computed based on the maximum value of fault index in first cycle multiplied with a factor K multiplied with maximum current in first cycle multiplied with factor. So where K is the rise factor and factor is 2 if rise value is less than 3. If rise value is greater than 3, the factor value is significant value of maximum fault index in a capture window divided by largest integer less than the significant value. Largest integer less than the significant value. So how do you compute the ratio value? The ratio value is maximum fault index in a captured signal divided by maximum fault index in first cycle. This is the ratio value. So based on that ratio, so we take as a capture factor value 2 or otherwise this. So this is the model which we take it for transient analysis or fault analysis in the system. So this is the model. So here we created as a interturn fault in R phase. So that we are observing here interturn faults in R phase. So this is the R phase. We created a distributed model. So we represent the interturn fault between these two windings. So this is one part of winding, this is another part of winding. So the entire winding is divided into two parts. So magnetizing component is also we are dividing here, two parts. One for the first part, another for the second part. But the rotor side, we don't have any change. So that we are keep it as it is for the rotor leakage inductance. But the rotor resistance, there is a change. So whenever the fault is happen, so we represent as a the component corresponding to the unbalance in the system that indicates as the double revolving theory. So according to that, the slip value is changes instead of RR by S, its value is RR by 2 minus S. So this is corresponding to the negative sequence component introduced in the system. So the next is the LG fault. So another is the line to line fault. So make use of the new algorithm. This is the healthy case of currents. So here the three-phase currents is captured. Make use of the practical system of DIP 8000. So with the help of that, we take it as the three-phase currents with a sampling frequency of 6.6 kilohertz under LD condition. So once we capture the current signals, those signals is sent through the SWT for reconstruction process. So what we require for the reconstruction is nothing but as the extraction of feature for the three-phase currents. So here we looking the current signal is corrected with certain noise. So we eliminate that noise, make use of SWT technique. So with the help of that, we reconstruct the signal. Here we looking the sinusoidal signal with this smooth line. But here we looking this, it's not a smooth because the noise is along with the sinusoidal supply signal. So under the healthy condition, we reconstruct the signal. That reconstructed signal is, we call it as the residue current. For these residue currents, we compute the detail level coefficients. So once we get the detail level coefficients, then calculated the slope of detail level coefficients. Those are the variation of slope of detail level coefficients of R, Y, and B. So once we get the slope of detail level coefficient, we take the absolute sum of three-phase slope of detail coefficient is set as a fault index. So this is the fault index variations with respect to the time. So those values is compared with the adaptive threshold. Here under normal condition, the adaptive threshold value is obtained as 4.93E09 because it's a residue value. Because of that, we get as a very less component of threshold value, that is 4.93E09. So the fault index values is less than this threshold. Because of that, this condition is, we call it as a healthy. So similarly, we take as the another case of healthy with 2% of supply unbalance. So in case of balanced supply, the fault condition is a fault or healthy is identified from the algorithm. Similarly, if 2% of supply unbalance is there, if 2% of supply unbalance in the currents is the similar nature with the incipient faults in the R phase or Y phase or B phase of the stator winding. So because of that, we check the healthy case with 2% of supply unbalance. So make use of this, reconstruct the signal. So these are the reconstructed signal of three-phase currents, and this figure shows the slope of detail level coefficients of reconstructed signals of three phases and fault index and threshold values of healthy condition with 2% supply unbalance. So even the supply is having certain unbalance, also the fault condition is not detected here because it is a healthy condition of the system. So the next is the interturn fault. Detection of stator interturn fault with the noisy condition is a crucial one. So because of that, we implemented the new algorithm. So with the help of new algorithm, we check with this. So here, this figure shows the 8-turn short circuit fault or 8-turn interturn fault in R phase. So for this fault, these are the currents. These currents is we send through the SWT for reconstruction process. Then we obtain the residue currents. These obtained residue currents is again decomposed and compute the values of slope of detail coefficients. So these are the three-phase detail level coefficients of slopes. So with the help of this detail level coefficients, we compute the fault index value. So the fault index value is this curve. And this curve indicates the count value. So from this point onwards, the window is take it as the 10 samples. And how many samples? So window of 10 samples, we will take it to count the fault index value when crosses the threshold. So every crossing point of fault index will give the one count value. But here, there is no crossing point. Starting point is here. From this point onwards, the fault index value is crosses the threshold. From this point of onwards, the window will give as the, so from this instant onwards, the window will give the count values. So that's why the count value slowly rises. So rises and crosses the threshold point. So when this count value is more than the 6 for the 3 successive samples, then the fault is identified. This is the count value of 6. So here is the instant we identify the fault index. So make use of this detection of stator interturn fault with 8 turns is effectively identified with the algorithm. So even that algorithm is identified with 2% supply unbalance or not, that we have to check with the help of these conditions. So this is the another case. So 8-10 short circuit in OR phase with 2% of supply unbalance. So even the supply is also unbalanced also, the system is identify the fault. So these are the simulated results. The same thing we have to simulate, validate with the help of 3 HP induction motor of experimental setup. So the experimental setup is made with the help of 3 HP, 3-phase, 440 volts, 50 Hz, 4-pole induction motor with 36 loads, 6 coils per phase and 72 turns per coil is considered for experimentation. So for the creation of the faults, we take it as the 2 tappings per phase or brought out from the machine from the neutral point. For each tapping have a resistance value of 0.1 ohm. So make use of that. We create the interturn faults and line to ground and line to line faults. So practically the interturn fault is we created with the help of tappings, bring it out from the neutral point. So this is the practical captured signal, and this is the reconstructed signal, and this is the slope of detail coefficients of reconstructed signal. And this is the fault index and count values corresponding to the 8-turn short circuit in OR phase. So like that we created the various faults and compare the fault detection criteria for various practical and simulation cases. So here these are the readings corresponding to the practical and these are the readings corresponding to the simulated. So this is the 2-turn. The first row indicates the 2-turn fault. This RMFI means, so this is a relative measurement of fault index with respect to the normal value. So normal means healthy value. So with refer to the healthy value, the relative value of fault index corresponding to the 2-turn fault is this. Similarly, we compute the relative value of adaptive threshold with respect to the normal. So whatever the adaptive threshold, we get it for 8-turn fault. So that is divided with the normal value. So let us we see here for the case of so here how much we get it, 1 point threshold, adaptive threshold is 1.465 E08. For the normal case, so what its value, 5.67 E09. So this value is divided with that value. How much we get it? So let us we take a calculator and compute that. So the value is 1.465 into 10 power minus 8. So this divided with you write down 14.65 divided with, so here 5.67. 5.67. So how much that? 2.58. So its value is 2.58. So it's a simulated value case. It is 3.52. So basically I'm taking that is 2% of unbalance, I think. Okay, 4.93 is correct. Divided value must be 4.93. So 14.65 divided by 4.93. So its value is around 3. So here it is 3.25 or something. So certain 8-ton faults on simulated results is 3.52. So like that, here practical case 3.25. So 2% case, it's nearly equal. So like that, we are comparing the fault in detection criteria for various practical and simulation cases. So all these are the comparison of values for missions of 5 HP and 3 HP missions. So these are the related publications. So this is for 10 HP setup, and these are the results corresponding to the fault detection algorithm. So coming to the conclusion of detection algorithm, the proposed fault detection algorithm using DW2 has been tested for various incidence angles, and the exhaustive simulated studies prove that the proposed algorithm is effective in detecting various faults. However, it's failed to detect the fault under noisy conditions. So another proposed algorithm of SWT and DWT is developed to overcome the drawbacks of DW2 based method, but the simulated results will give the efficacy of the proposed SWT when compared with the DWT. So this method will give us a effectiveness with the help of comparison of the results. Even the detection algorithm is effectively identified in the presence of noise. So coming to the classification of various disturbances, so we take as a supply side faults and stator faults. So all these faults we must effectively identify which type of disturbances happen on the mission. So that information is give it with the help of the techniques we adapted with the systems like as a human, so that we call it as the artificial neural networks. So with the help of artificial neural networks, we can classify the various disturbances. So disturbances like as stator interturn faults, stator line to ground faults, stator line to line faults, and then again which phase will involve that disturbance. So such information is we get it by using the classifiers. So here we use it as the ANN classifier is used to identify the disturbances as well as the stator phase faults, then stator interturn faults and its severity. So the severity level is 2 turns or 4 turns or 6 turns or 8 turns. That also we identified, make use of classifier. So for that purpose, we require the features. So whenever we implement a classifier, so we require the features. So what purpose we use the classifier? So fasten the process. So we apply the condition monitoring technique. So without delay, we can identify the which type of disturbances happen on the system. That identification needs as a classifier. So here we use a disturbance classifier as a ANN. So whenever we take as a any classifier that needs a features. So based on the features information only, the classifier will give the classification. So here for the disturbance classification, we take it as the 9 features for various disturbances. So all these 9 features is the the mean, deviation values and maximum values of the coefficients. So the feature 1, 2, 3, 4, 5, 6, 7, 8, 9 are defined as the standard deviation of R phase deviation, Y phase deviation, B phase deviation, maximum value of R phase, maximum value of Y phase, maximum value of B phase, mean value of R phase, mean value of Y phase, and mean value of B phase respectively. So what is this mean value? What is its maximum values? So which coefficients of features we have taken to classify the disturbances? So the variation of A2 coefficient is taken as the features for the disturbance classifier. So here we take it as a one cycle of window. In this one cycle of window, we compute the standard deviation of R phase signal, standard deviation of Y phase signal, standard deviation of B phase signal. Similarly, we take the peak value, maximum peak value, either positive cycle or negative cycle according to the disturbance. So which cycle value of peak, so is considered as the feature that is based on the absolute. So absolute peak value we are taking here. So based on that feature, we classify the disturbance. So totally we take the 9 features, standard deviations of all 3 phases of A2 coefficients of reconstructed signal, all the 3 phases of absolute maximum values of A2 coefficients. Similarly, all the 3 phases of mean values of A2 coefficients. So those are take it as a disturbance classifier of input. So this disturbance classifier classify the disturbances. So total disturbances considered in this method is 6. So the C1 is single phasing, C2 is sudden load change, C2 is supply unbalance, C3 is under voltage, C4 is sudden load change, C5 is stator interturn fault, C6 is the stator phase fault. So whenever the defaults is a stator interturn and stator phase faults, we require the another classifiers. So again, the stator phase faults is 12 types. So R2Y, Y2B, B2R, so that is one. Similarly, we have a line to ground fault of R phase, line to ground fault of Y phase, line to ground fault of C phase, interturn fault of R phase, interturn faults of Y phase, interturn fault of B phase. So interturn faults is again according to their severity, we classify into 6 levels. So these 6 levels indicates the what is the severity of the faults. So these 12 indicates as the severity of the stator interturn faults. These 6 levels indicates the stator phase faults. So line to ground of A to G, B to G, C to G. Next, line to line fault of R to Y, Y to B, B to R. This AN and 3 will give us as a classification of stator interturn faults of R phase of 2 turns, R phase of 4 turns, R phase of 6 turns. So like that, we have a 4 levels of interturn faults, 2, 4, 6, 8, like that 3 phases. So 3 fourths, 12 classifications. So the training and testing data is required for the ANN. So overall generating data, the 75% is given for the training and remaining 25% is given for the testing. So here the training and testing data is created, make use of simulated results as well as the experimental setup. So make use of experimental setup. These are the data generated for the training of the ANN. So these are the data patterns generated for the simulation. Similarly, these are the experimental and simulation patterns for the testing. So 858 patterns is given for the training of ANN and 429 patterns are given for the testing. So for the finding as the efficacy of the trainer, we take it as the different hidden layers and different epoch values and different learning rate and momentum values. So because of these variations, we get the effective trainer. So that effective trainer given by the system considered for classifier is the 1420. So here the ANN is designed as a multi-layer. So layer 1 must have the 11 neurons and layer 2 must have the 20 neurons. With the learning rate of 0.4 and momentum value of 0.69 will give the testing accuracy of 90.68 with the training time in seconds is 54. And another is 1420 and the learning rate is 0.5, momentum value is 0.68 and the testing accuracy is 91.38 with the training time in seconds is 86. So this is the test performance we consider for the system. So because of that we consider as a 1420 is the best. So even 1410 we are observing for the different values of epochs. This will give the higher and this will give the lower accuracy. Because of that we go with the 1420. So the double layer ANN of 1420 is considered with the learning rate of this and momentum value of this. So which will have the less time in the representation of the system. So the less time is taken for the system of 0.4 learning rate. So because of that we consider this is the best performing the system. So make use of that the sensitivity, specificity and average values of disturbances we get like this. So next we go with the MNN. So MNN is a modular neural network. So artificial neural network of feed forward approach is used to classify the disturbances in this proposed method. So coming to the MNN structure, this MNN is a modular neural network. So the network is divided into different modules as for the requirement of classification. As for the requirement of classification. So basically this neural networks are divided into two main categories. So one is the monolithic networks and another is the modular one. In canonical implementation, most of the systems employed as a monolithic networks in order to solve the given task. So this feed forward neural network is a monolithic pattern of representation. So however, we solve the large amount of data and problem is highly complex. So that means the disturbance features is very near for the certain cases. So in that case, the classifier efficiency is not good. In such cases, we require the modular pattern of classifier. So in order to overcome the shortcomings of ANN, so the modular approaches is we use. So in the modular neural network, the major benefit is it reduces the complexity happen in the training. So because we split the network into small modules. So whatever the network we consider in the food forward, but in that network, what we do it, so a single network will train the all the 6 types of disturbances. So the targets is all the 6 types of disturbances. But here the target we give it for the modular network is a single target. So like that we represent as a 6 modules of FNN, feed forward neural network, and the results of those modules is given to the max of individuals. So we give it as a 9 input as a system of 9 modules. Sorry, not 9 modules. The disturbances is 6. So the 6 modules of FNN of inputs is 6. So those 6 outputs is given to the mux, and we get as the final classification value. So in this process, we test the system with the previous data generated in the ANN. So the same data we give it for the modular neural network, and the performance of the system is we represented with the help of confusion matrix. So this matrix is, we call it as the confusion matrix. So this C1 is a type of fault, that is a stator supply side fault. So that is a single phasing fault. So the number of single phasing faults we give it for the system for testing is, so earlier we representing here in the how many single phasing faults we are giving for the testing is, so 20, but out of 20 it's given as the 21 for the single phasing faults, and the same single phasing fault is given for the that another fault. C2 fault is like as a C1. So like that it's given sum is true and true. So that means it's a single phasing fault as a recognition of 21. That we call it as the true positive. But here the fault is a C2 type fault, and it's identified as a C2 of 50 patterns. So remaining is, it's not a C2, but it's identified as a C2. Similarly, this fault is also not C2, but as identified as a C2. Like that it's given. So that we all call it as the false negative. So true positive, true negative. True negative means it's a stator fault, but it's identified as another fault. That is, we are saying as the true negative. True negative. So false positive, false negative. Similarly, true positive, true negative. True positive, true negative means it's a negative fault and identified as a negative fault. Positive fault, and it's identified as a fault, then we call it as the true positive. So accuracy of the system is, we computed make use of this algorithm formula. So that is total positives plus or true positives plus true positive divided by total positives plus total negative. So the total positive have as a combination of true positive plus false positive, and total negatives as a combination of true negative plus false negative. So these are the informations of training of MNN. So compare with the ANN. So the sensitivity values given by the ANN is 0.85, but MNN is given as the better sensitivity when compared with the ANN. Because it's a modular, because of that the complexity for training the algorithm is less for the modular neural network. So similarly, we go with the identification of phase faults and identification of stator interturn faults. But the features we given for the ANN is different. So ANN2 is this structure. It's also two-layered feed-forward neural network. The inputs given for this structure is absolute values of maximum slope values of detail level coefficients of R, Y, and B phases. So the classifier of output is the phase faults of RY, YB, BR, RG, YG, and BG. So this is the training patterns and testing patterns. This is the accuracy of ANN2. So the same ANN accuracies we compare with the modular classifier, and the accuracy of modular classifier is 93.94. So that means it's improved the classifier performance when compared with the feed-forward neural network. So the modular neural network of accuracy is more when compared with the ANN2. Similarly, for identifying the faulty phase and estimating the severity level, so we extracted the features from the slope of detail level coefficients. So make use of that information and the mean energy values of different levels of stator interturn faults as take it as the input for the features. So for the feed-forward neural network of multi-layer. So here also we take it as the two-layer feed-forward neural network for the input patterns of maximum slope of absolute maximum slope of detail level coefficients of R phase, Y phase, B phase, and mean ratio of A4 approximate coefficients. Mean ratio of A4 approximate coefficients. And the output we get it from this network is the level severity level and phase identification of stator interturn fault. So there are the 12 levels of faults we represent from that network. 2-turn short circuit in OR phase, 4-turn short circuit in OR phase, 6, 8 turns in OR phase. Similarly, 2, 4, 6, 8 in Y and 2, 4, 6, 8 turns short circuit in D phase. So these are the testing, training and testing patterns. And the confusion matters given for the ANN3 of efficiency is 95.73 and modular network of overall efficiency is 96.5. So the efficiency of MMN is better than the ANN of even third classifier also. So from that we conclude that the considered distributed model is valid by comparing the frequency responses obtained from the simulated and experimental setup. So the two-port algorithms are proposed based on the three-phase measurements, and DWT is failed in the presence of noise conditions. But the second algorithm of SWT and DWT based approaches effectively identify the faults even under the presence of unbalanced. So by introducing the modular concept to the neural network, so classification of disturbances and identification of stator faults and its severity levels is identified accurately even the system is complex. And the performance improvement of the modular neural network for different classifiers is 2.33% for the classifier 1 and 8%. So this ANN is classifier is improved as the performance of 2.33 for disturbance classifier and 4.55 for the classifier 2 and 1.17 for the classifier 3. So the future scope for this area is the algorithms is tested offline on a practical motor of 3 HP and 10 HP, but it's not not extended this for the online. Because of that, there is a scope for extending for the online condition monitoring. So, and one more thing is this protection schemes is tested for low voltage motors also, but the same algorithm can be extended to the medium to high level motors also for the further studies. So these are the details of publications regarding this presentation of work. And now I show some simulations regarding the model for measuring the impedances and measuring, creating the faults on the three-phase induction motor with the help of high frequency models, high frequency distribution models. Okay. So now I stop sharing this presentation window and show you as my MATLAB window. Now I'm showing the Sir, can I share my entire window?
Yes, madam.
Is it possible? Is it possible?
Yes, madam. Yes, madam. In sharing, first one you are getting entire, next one you are getting tabs.
Okay.
It's visible, madam, MATLAB.
Okay. And common mode of number. So this is the common mode. In common mode representation, the system is connected between the measurement of device for the all the tied phases of 3 and ground terminal. So this is the ground terminal. So one terminal is measuring for the impedance as a ground. Impedance measurement for another terminal is the tied terminals of these three. So that's why we connected here for measurement of the impedance. Okay. So exciting this with the single phase value, because whenever we required as a measurement of impedance, we require the ratio of voltage and current. So in the MATLAB, that voltage is given as a single phase supply for this circuit, because we tied all the three phases. So that's why we give it as a single phase supply here. And you represent as the measuring one, that is the in the continuous mode, and connect the impedance measurement here between the terminals of tied values of three phases and ground. So now we have to run this file and see the impedance plot. So for measuring as the impedances or FFT analysis, we require the power GUI block. This block is essential for measuring the impedances and then FFT analysis, steady state analysis of the any analysis, we require this power GUI block. So double click this and go to the tools. Here tools, we see the steady state, initial state, mission initialization, impedance measurement, FFT analysis. So here various uh, analyzing methods is there. Even load flows also executed with the help of this Power GUI block. So now here our requirement is the measurement of impedance. So we go with the impedance measurement. So we can see the impedance measurement from the frequency range of 200 in steps of 10, 100 hertz up to 1 megahertz. So this is the scale we consider for the frequency of x-axis, and y-axis is the impedance value, magnitude of impedance value. So the lower plot indicates the phase versus frequency. The upper one indicates the magnitude of impedance versus frequency of variation. So even in our presentation also we discussed the similar thing. In the common mode measurements of 3 HP. So this is 5 HP, but we are open the 3 HP mission. So this is the differential mode, and this is the common mode for the representation of impedance value. So the same impedance plot. Okay. So here we are looking the similar thing. So this is the magnitude of impedance. Okay. So next one is the phase value. So phase versus frequency. So in the simulating results, we get like this. So here also it rises up to the value of 0. Here the value is near to the 120 minus 120 degrees. So it is 100 and minus 80. That is 90. Minus 90 is this flat value. So this flat value is corresponding to the minus 90. So at resonant condition, this is the point corresponding to the resonant condition of the system. So at resonant condition, that will gives us the 0 value for phase. So at the point of resonance, its value is 0. Phase angle is 0 because it's a pure resistance. The circuit is offers the pure resistance, and voltage and currents are in phase. The phase angle value is 0, 0 degrees. So at the resonant condition, we are representing it is 0. So anti-resonance, we have the another point. So this is another point. These are the two, resonance and anti-resonance points. So based on those information also, we estimated the parameters. So next is the differential mode representation. In differential mode representation, whatever the parameters we obtained from the practical data, the same parameters is we incorporated here and created the distributed model. For this distributed model, so we excited with the line to line values because the impedance measurement is connected between the terminal of A phase and tied terminals of B phase. So this is the B phase. So B phase tied terminals is connected as a one terminal measurement. So another terminal of impedance measurement is connected to the A phase. So this is current measurement. So the impedance measurement will require the current measurement as well as the voltage value. So these two ratios will give the impedance value. So we run this, we can see as the, so here already we have the open plot of this power GUI. Because of that, it's given as a error indication. Again, differential mode of practical error occurred at You open the differential model. So we can open the 5HP even. It's also distributed model. So this is the impedance curve corresponding to the 5HP mission. So this is the measurement. So here one terminal is connected to the A phase. Another terminal is connected to the tie terminals between the A and B. So for that we get as the impedance measurement. Okay. So next we created the faults. So at the turn level we created the distributed parameter model. So here we created the distributed turn level values. So this is the distributed turn level values of stator winding. So here the stator winding is created as a coils like this. So how many coils we have created? We created 6 coils here. Coil 1, coil 2, coil 3, coil 4, coil 5, coil 6. So again this coil 6 we have created as the another 1, 2, 3, 4, 5, 6, 7, 8, 9. So this coil will have a turns of, again that coil will have a 9. So each 9 will have a again 1, 2, 3, 4, 5, 6. So 6 nines 54 tons. So each coil is contains the 54 tons. So like that we model the each coil here. But remaining coils we take it as a lumped one. So only which coil we have created the faults, that corresponding coil we have created the distributed model with the turn level of 54. Turn levels of 54. So here the fault is created with the help of breaker. Fault is created with the help of breaker. So here switching intervals is we give it here 19 by 60. 19 by 60. Okay, so like that we give it as the at which instant the switching action is happen for the circuit, that we are given here. So the instant we represent as the 19 by 60. So out of 60 cycles, at the cycle of 19th, we have created the fault with backer resistance of 0.001 and snubber resistance of 2E5. So we run this simulation with the 10 by 60. So we represent as the 10 by 60 here. Volt with the time interval of 5 by 60. Okay, sorry, this is not that. So this is the switching instant I given. So after fourth cycle, the fault is created. With the help of TA1, I am given as the externally TA1 is the instant of 0, 30 degrees. So the step values I incorporated. So the fault is not clear within the cycle. So that's why I'm given as the 19/60. So the fault is happen after fourth cycle of the simulation. So overall cycles is 10 and fault is sustained up to 10. So like the default is given for the circuit. And other we represent this is line to ground. So we created the line to ground faults like this. So this is one coil, that coil to ground. So sixth coil is the end to the neutral point. Because of this one coil to ground fault, two coils to ground fault, like that we are representing the coil to ground faults. And here also we represent the similar way for the coil to ground faults. So inside that, so we represent as a lumped representation. So only here we represent the turn level representation for this. So it's a 54 turns for each coil. So it's given as a error, TA1 does not exist. So because of that, it's not executed. TB2 is not given, TB1, TC1. So those values is not given. So because of that, it's given as the error. So I defined these variables. So those variables is given for the convenience of simulating the different switching instance. Let us, I represent TA1 is 0 degrees and TB1 is 100. So that means so I'm not creating any interturn fault in B phase. Similarly, TC1 is 100, TB2, TA2, TA2 equal to 100. So TA2 equal to 100 and then TB2 equal to 100 and TC2 equal to 100. So because I am given as a large value for taking any switching instant for the circuits. So now we once again simulate this and we see the any error. So TB3 is there. So that means line to line faults and line to ground faults is also represented in this system. So TA3 equal to 100 and TB3 equal to 100 and TC3 equal to 100. Okay, so now we simulate this. TB4, TC4. Okay, so we have some other also. So we give it that also. TA4 equal to 100, TB4 equal to 100 and TC4 equal to 100. Up to 6 levels, we have created 6 parameters. So we give it as TA5 equal to 100, TB5 equal to 100, TC5 equal to 100 and TA6 equal to 100, TB6 equal to 100 and TC6 equal to 100. TA. Sure. So we created the fault at the instant 4 by 60. So fourth cycle, after fourth cycle, we created the fault. So this is the reference. This is 1, 2, 3, 4. So this is the instant the fault is created. So we observe here the fault is created. So this is our voltages and currents. So 54 turns is short circuited in one coil. So one entire coil is short circuited. Because of that, we get the huge current change in the that corresponding phase. Okay. So this is the phase corresponding to the OR. But here the color indications is different. But we are created in the OR phase. Okay. So here power GUI is there. So based on that power GUI, we can see as the what is the steady state values. So we observe the steady state values corresponding to the power GUI before the fault. So here it's given as the measurement values corresponding to the system. So voltage values, voltage measurements we connected in the each coils. So based on those 10 levels of voltages is also given here. So those 10 levels of voltages is 5, 0.94 volts under the steady state, and the overall voltage of each phase here it's represent a line to line value. Because of that, the peak values given for that is 370. So the measurement is given as 375.59 at an angle of 0, 375.59 at an angle of minus 120, 375.59 at an angle of 120. So each other is displaced by 120 degrees. So that is measurements corresponding to the voltages. So stator winding coil. So this coil 1 of voltage measurement is represented in the stator windings of R, Y, B. So those coil level of voltages is represented here. So like that we have to see the informations. But in the analysis part, we need the current signals. So these current signals is we send to the wavelet transform. So now I will open the wave menu. So in this wave menu, we apply the one-dimensional signal. So this wavelet transform is we apply for the one-dimensional signal. So for one-dimensional signal of wavelet, so we open this. File, import from the workspace, import signal. So we required IA1, IB, IC, so like that. So we have different currents. So let us we take the current of IA. Okay, so IA current is this. So we apply the mother wavelets of Hor, Debachew, Simulate, Coflet. These are the different mother wavelets. For single dimensional signals, we generally use to analyze the fault analysis for Debachew, Simulate, and bioorthogonal. But in my work, I apply the bioorthogonal 5.5 and up to the level of 4 and analyze the signal. So this is the detail level coefficient without incorporating any noise or injecting any noise to the simulated circuit. So without noise, the detail level coefficient sharply give it the value. So it's give it at the instant of 400. So per cycle, how many samples it's created? The sampling frequency is the frequency of the system is we consider as the 60 Hz. Because of that, the simulation time is we give it as the 10 divided by 60. So 10 cycles we simulated for the 60 Hz supply of signal. So the sampling frequency we give it for the measurement is we see here. So the sampling frequency is 66 kilohertz. That means per cycle 100 samples is generated. So we created the fault at which instant? We created the fault at fourth cycle, 4 into 100 samples, 400. So at the instant of 400 sample, the fault is created. That's why we get as a higher value of detail level coefficient at that instant. Remaining all instant, we get the 0 values of detail level coefficients. So disturbance corresponding point is we get it from this. So another is reconstruction of the signal, make use of SWT of denoising of the single dimension. So here also we download load the signal, not load, import the signal from workspace. So import that signal. So we take this signal and apply the Bior 5.5 and the levels of 6 and decompose the signals with the help of soft threshold or hot thresholds. This is the default values. So you select as the decompose the signal. But here the number of samples of this signal is not the 2 power level, so that's why it's not given as the analysis. So always this signal says represent as the 2 powers of values. So instead of 1001 samples, we require the 1032 or 30, 1320. So like the 2 power values must be required as the samples. Otherwise, it's not decomposed. So let us so I extend this sample values, make use of this IA signal. So this is the IA signal. So 1000 so I extend some samples here by copying this. 1, 2, 3, 4. Control V and remove one sample. Delete row. Okay, now again we import the signal from workspace by taking this. Ten 24 is the length required for this. So we copy and paste its values up to 1024. Three more is required. Okay. So now load it, the signal. Okay. Now load it the signal and then decompose the signal. So this is the decomposed signal. Here we required only certain values for denoising the signal. Here noise is not there, because of that any detail level coefficients corresponding to the levels of this. Okay, so if noise is present, we require the certain noise in the detail levels. Those noises eliminated, make use of the information we incorporated in the system. So these are the thresholds. So we select as the non-white noise, unscaled white noise. So like that, and you change your noise levels also. You remove all the coefficients corresponding to the D5, you can remove it, or you can exit the only that and remove the all the other levels of signals of detail coefficients, we remove that. So these are the levels corresponding to the approximate. So because of that, I am not changing any information from the approximate coefficients. So independently for the detail level coefficients, so we incorporate this for removing the noise at the edges also. Okay. Yes, we fix the threshold. So this threshold level is instantly changing. So denoise the signal. So denoised signal is this. So from this, we looking as the observation of these points and export this signal to the workspace as a denoise signal like this variable, and decompose that once again from the DWT for further analysis. So like that, we have to implement the algorithms. So the features of that detail level coefficients or approximate coefficients is given to the classifier and classify the disturbances. Okay. Any doubts?
Madam, thank you very much, madam, for a clear-cut explanation about the modeling and implementation of the three-phase induction motors, parameter estimation, classification of the faults and implementation by using the MM and ANN techniques. And we are very grateful. You are presented very well manner, more than 2.5 hours with very patience and commitment. In this, now we are allowing to all the participants to unmute yourself. If you have any doubts, so please you can ask directly. సార్ కార్తీక్ సార్ అందరికి అలో చేస్తారా కొంచెం people. Okay, madam. Nobody is responding. We will end the session now, madam. We'll close the session.
Okay, sir. Thank you.
Madam, thank you. Thank you once again. Thank you, madam. Thank you very much on behalf of the EEE department, faculty, and students. Once again, thank you very much for accepting our invitation to access to the resource person and presenting in a very well manner. Once again, thank you very much, madam.
Thank you, sir. Sir, shall I leave?
Yes, madam. Please close the. Okay, you can leave, madam.